time. Welcome everyone to today's string seminar. We're very happy to have Arindam Bhattacharya with us. Going to tell us what renormalons as saddle point.
Uh, Thank you for the opportunity to present here at ICTS. What I'm going to talk about here is this work which I've been doing with my advisor, Matt Schwartz at Harvard, along with Jordan Kotler and Orlin Dorsey, on understanding these objects in precision QCD phenomenology known as renormalons, and trying to connect this to saddle points in the path integral, so that you can put them on same footings as objects such as instantons. So for the next hour or so, I want to briefly walk you through to what these objects are and how we understand them as saddle points. So my brief outline for the talk today would be to first talk about how these two objects actually appear. So both instantons and renormalons are part of what are known as asymptotic series in quantum field theory and quantum mechanics. And the way they practically show up for actually dealing with phenomenology is to actually, they obstruct what's known as Borel resummation. And I'll talk about what Borel resummation is, why this works in quantum mechanics and quantum field theory. And following that, I'm going to connect Borel resummation to what we know as saddle points in the path integrals, for instance, instantons and other generic saddle points or saddle point approximations of the path integral. Following that, I'll talk about what these renormalon objects are and connect them as saddle points by showing eventually that renormalons can also be understood as saddle points of the one loop effective action in the path integral. So two very different objects, very different phenomenology, but can be understood in the same language via the path integral as saddle points of appropriate actions. So perturbative computations in field theory gives asymptotic series. This was something which was very disconcerting for me to learn when I first learned about this during grad school. And the fact that even if you try and compute physical quantities as a function of the coupling or alpha, which is Paul for weakly coupled theories, even if you were able to compute this series to as high orders as you want, generically these coefficients, this series does not converge. And this was actually known way back. Like Dyson showed this in 1952. Was the fact that like these CNs generically do not converge. This series is not well defined. And contrary to most of his work, this was a very physical argument that he proposed, which was the fact that if you assume that this series had an open set of convergence on the complex alpha plane, you got very different series for positive coupling versus negative coupling. For instance, in QED, with alpha greater than 0, we get an attractive force between the electron-positron pairs. You flip the sign, you get a repulsive interaction. And this fact here kind of makes vacuum unstable. You can randomly pop out a lot of positrons and electrons and widely separate them. And this makes the theory unstable there. So it's very different physics of one side to the other one. And that kind of convinced Dyson of the fact that like there wasn't any open set region of convergence of this series at all, even for QED. And this is, the lore is that this is generically true, but there is no rigorous proof of this. So I'll take this as an assumption, which is the fact that series in QFTs and perturbative QFTs, even if they are weakly coupled, give series which don't converge. And these are what are known as asymptotic series. So, yeah. Yeah, so that's the next slide. So we want to understand how badly they diverge. And a toy example, which I rather like to play with, is this 1D example series here, where I have this function, which I know to exactly compute. And I can actually also obtain the series expansion of it. And what we find is that we get factorial growths, where this CNs in particular at the nth order, at large enough n, they blow up factorially. So there's like n factorial growth. But also there is this geometric factor a to the power n, which kind of dictates that if for instance, for this function here, if you look at the difference between the exact function and its asymptotic expansion, you would find that eventually it starts at low enough orders, there is some sense of convergence here. But eventually, at a critical point where this is n star, which is of the order of a alpha to the 1 over a alpha, the series eventually begins to diverge. There's this rather funny rule in divergent series known as Carrier's rule, which he says that divergent series actually converge faster than convergent series because they don't have to converge at all. And this is kind of generically true even for like the field theory examples that we know of. So I've reduced this to a 1D example, but eventually I'm going to get to the point where I show that this is actually very generic even in field theory or quantum mechanics. I am not sure of that. Yeah. Okay. But it's a good question. So far, I am not aware of field theory examples which are faster than factorial growth. I'm not sure if this is the most badly divergent behavior that is possible. But
I think there are generic arguments from
yeah,
counting Feynman diagrams that 50 you cannot.
worse than this one, right? Yeah. So as somebody who does precision theory, like part of my other job is to actually start computing these terms. Something which I want to practically deal with is the fact that like if I know at the onset that this series is eventually going to diverge, can I assign a physically appropriate resummation principle where I can still get something which converges, which has these initial, whose expansion has these initial points which I can verify, but I get a result which makes sense. Optimal truncation is one method which people resort to, where you kind of just cut off the series at the point where it begins to diverge. But it's not super intuitive or rigorous. It's more of a cop-out way. So you want a resummation technique which kind of not only resums this series when Cn is convergent, but also works for divergent series by giving them an appropriate meaning. So what do I mean by that? Yes. Yeah. They're not gonna, yeah, right. QCD, this factorial-like behavior actually already creeps in at fourth or fifth order terms, which is state of art right now. I'm gonna get to the pheno part where like eventually, like this is not just a theoretical in like question of this is of rather practical relevance where you have to come up with schemes which basically are aware of this factorial blow up and they kind of remove it by hand. Or they're sorry. It's a very diagrammatic answer. So I'm eventually gonna get to the point where I wanna basically where I want to show that like this is not just something diagrammatic. It's seen in the path integral directly. Okay. So I want to talk about this technique called Borel resummation, which basically assigns a meaning to these divergent series, factorial divergent series. So what does one do? We start with this series f alpha, which is Tn, which could be factorial divergent. I'm going to generalize the exponent to have, like, say, instead of just being an integer, there can be other numbers out here. I'm going to make it n plus a. So you divide out by the factorial growth. You know that like it's going to be factorially blowing up. And you obtain what's known as this Borel transform, d of f, where you take these functions Cn, you replace alpha by this variable t, and you divide out by the factorial growth. So if here, if I set a equals 0, the gamma function actually just reduces to the factorial growth. So you could, in principle, you could also get like alpha n plus half, alpha n plus 3/4, and so on for some 1D integrals. It's just trying to be general about it. Usually we don't encounter those exponents. Yeah, or like at what order does the leading order start in some sense? Yeah. So you get this Borel transform here where I am dividing out by this factorial growth. And what one does thereafter is to introduce this leap of faith, where you see that once I obtain this Borel transform B of f, what one tries is to do the Laplace transform of this function. So this is nice because if you formally expand this series in T, you can check that this integral, the formal expansion of this integral in alpha, agrees order by order with the, and if the integral exists, it assigns some meaning to this divergent series. And as any summation rule, if it converges for convergent series, so the valid summation technique that people use. So I can give you an example. Let's go back to the factorially diverging alternating series in the previous slide. So my geometric growth is now alternating. It flips between positive and negative signs. If you compute the Borel transform, you get this function 1 over 1 plus 80. It's just a geometric series at the end of the day. And fortunately for positive A, I can actually do this Laplace transform, and I get what are known as these incomplete gamma functions. So in the case of factorially diverging alternating series, Borel resummation actually works. It gives you a function whose asymptotic expansion agrees with the series that you have computed, and it gives you a function, and the function is well defined, and you can physics with it. But so alternating factorial blowups, which is the case with QED, for instance, can be resummed using Borel resummation. But for other theories like QCD, sometimes even this fails. So the classic case is if I have the factorial growth, but I have a positive geometric growth associated with it. In this case, if I compute the Borel transform, I'm going to get a function which looks as 1 over 1 minus a of t. Now, I can't do this integral anymore because I'm on the positive real axis and I have a pole which is obstructing my resum. So I can't construct the Borel resummed function at all. And this kind of generic behavior is true for QCD, for instance. I'm going to show this in a couple more slides, that this kind of non-alternating factorial growth is to go, especially in asymptotic free theories. So the pole obstructs our resummation. As any good physicist, we try to avoid it. So we move the contour up and down. So give a slight epsilon to positive, move the contour up, so slight epsilon negative, I move it down. But this comes at a cost. My resummation can now be done. I'm avoiding the pole, but I'm ambiguous. The results for C plus and C minus actually differ by terms which are of this form here. So it's just the circulation of this contour around this pole at t equals 1 over a. And if I compute the residue at that pole, I get this form, which is rather characteristically the poster child of non-perturbative phenomena. You get e to the power minus 1 over a alpha, where this function famously does not admit a perturbative expansion. I can't expand it in alpha, even at small alpha. But crucially, this starts to look a lot like non-perturbative contributions. For instance, like instanton contributions in the path integral would look something of that form. Moreover, if this function a is beta naught, which is the first coefficient of the RG for the coupling alpha, you can reduce this exponential factor to the Landau pole in the IR. So this would be, for instance, lambda QCD. So this has, if A is beta naught, and I'm going to show that this is the case for Renormalons, this starts to look a lot like the non-perturbative contributions which you to account for, or like something which lattice would give. So e power minus 1 over beta naught alpha looks as lambda QCD over a scale. So it becomes a dimensionless ratio of the non-perturbative Landau pole, like the Landau pole in the IR over like the high energy scale of interest. Yeah. Say if you use the MS bar scheme. Yeah. So you define with 1 by alpha going to 0. Yeah. Yeah.
So you define it with the Landau pole.
With the Landau pole in the, yeah. Okay. So this is, as I said, this is generically the case for field theories. So as Raghu mentioned, there is this rather nice argument from Lipatov back in the day, which was that like in field theory, you kind of expect this factorial growth. And it's simply a consequence of counting the number of diagrams that you get from the path integral. So I'm going to make things simple, look at like a 1D example, which has the same. So that's something that I'm going to get to. So usually, say if I did not know how to evaluate a path integral non-perturbatively, but I can evaluate it perturbatively to as many high orders as I want. If I find that I have a factorial growth of a non-alternating nature, it can be the case that this, let me go back, this factor A is related to the action of the instanton or action of some non-perturbative saddle in your theory, which you're missing by just simply doing like a saddle point approximation near the free theory with some interactions. So you can gauge the presence of these non-perturbative saddles by looking at the high order perturbative behavior. So there is an active area of research called resurgence, which tries to study exactly this, where you want to infer eventually the presence of all non-perturbative saddles just from perturbative data. The function spaces that they study are very restrictive. I think algebraic functions of some form. And they've been shown, like resurgence has been shown in like quite some lower dimensional theories that this holds true for field theories where you can exactly solve for the partition function. Whether that is true for these asymptotically free theories is a question that remains to be seen. But that's something which we eventually want to explore, where we want to connect these ad hoc rules, which people have used in precision phenomenology in QCD for decades now, which have worked spectacularly well, like for instance, like have been checked from lattice. And we want to eventually connect this to the kind of mathematical tools or theorems from resurgence or some foliation of the path integral, which corresponds exactly to the kind of tricks that they have been doing to separate perturbative and non-perturbative contributions. Okay, so one generic source is the fact that the number of Feynman diagrams, if I compute for field theories, is generically factorially. It blows up factorial. So I'm going to give a 1D example, just a Gaussian integral perturbed by this 4-point interaction. I can actually do that integral for say alpha greater than 0, this Bessel function. Moreover, I can just expand this integral order by order in alpha, and I can obtain the series exactly. And if I look at large enough order n, I get this -3/2 to the power -n, and I have this factorial blow up. So why does this happen? We can formulate the same integral as we can assign Feynman rules to it. I can give a propagator, I can have an interaction with -alpha, and z of alpha then just becomes the bubble sum of the kind of diagrams that I'm looking at. And generically, with this form of interaction, the symmetry factor is going to be less than. So if I'm seeing this factorial growth, this is already telling me that the number of diagrams itself is factorially growing up on the example. And way back in 1976, Lev Lipatov had actually shown that like this kind of combinatorial blow up of the number of Feynman diagrams is associated with the. If I have an instanton in the theory, I'm kind of guaranteed that the number of Feynman diagrams that I'm going to get if I evaluate the partition function perturbatively is going to be factorially blowing up at each order. That's yeah. Yeah, that I am one-dimensional case. If I have an integral which looks of the form which is like an exponential, where I have like a function in the integrating variable over the coupling, I kind of know that I kind of know from complex analysis that it's going to be at most factorial divergent. Experiments tend to tame the factorial growth usually. They don't tend to increase it. Like bosonic variables make it more and more divergent. So at least for one-dimensional ones, I think like if I have something which looks like an exponential Laplace integral, I kind of know that it's going to be factorially blowing up. But whether the but that's a good one. Usually, I think so. I could take this integral, multiply it, square it out, and that's gonna yeah. Then you could get n factorial square.
That sounds like
Number of that's probably yeah. I need to check that one for like generic fields. The field theories that I'm going to be concerned with, I'll just have like a single field with an interaction with a coupling which is dimensionless.
power also becomes
Yeah,
Power squared
okay,
is
that's
also
certain.
power doubles
Yeah. Oh, yeah, sorry. Yeah. But like generically, like if you just look at the Feynman rules, you can see that like the number of diagrams are factorially blowing up. And I think there was all like even before Lipatov, for instance, in quantum mechanics, Bender had checked this by his recursion tools to like a really high order where he saw that this growth was like really. Whether there can be faster growth, I really need to check that one. Yeah, I'm not sure, but I'm gonna concern myself with just factorial growth so that like I know that Borel summation more or less works. Right.
and you have possibility of
Right.
okay,
sir.
decoupling alpha.
Yeah. I mean, the growth factor is related to, so, I mean, let me see if I get this one correctly. I like the alpha part is more or less fixed here, just by the form here. And the growth of the non-perturbative contribution is dictated by this factor A. Oh, it's everyone. Oh, okay. Okay. If you get.
Come to n factorial, then you can just
Yeah,
square root of it.
that's what I've seen
That's
so
what
far. Yeah,
happens.
yeah.
Same thing. Come to n factorial, you write a to the minus square root of a to the minus 2. Then in the subsequent formulas, square root of a and alpha. That's a special thing for closed string. Open string, the perturbation expansion. Actually, there's a family of Feynman diagrams you can draw that's n factorial or two rails.
Right.
And put n points on the top. Top is fixed, but the bottom you can permute in n factorial.
I see.
Way. That's at least n factorial diagram.
Right.
The top
Yeah.
n
Then.
thing that
Good. Yeah.
join in. And the claim I have it that's like generic.
Yeah, it's still, yeah. I'm like, I can, there is an alternate argument for that using level sets that I can actually show that like, even if I take multiple products of these, I'm still going to end up with factorial growth. Yeah, I'm not sure about like faster than factorial growth, how it relates to like amelioration of like the non-perturbative contributions. So, I'm going to sketch out Lipatov's argument for the field theory one and how it relates to instantons there. So what Lipatov did was the fact that like he looked at phi-4 theory, the Euclidean version of it, but critically with like inverted potentials instead of like positive lambda phi-4, I'm looking at minus lambda phi-4. And what he was concerned with was computing the partition function as a function of the coupling lambda.
Putting
Upside down, yeah. Is
Then
it,
you should have a plus sign in this equation.
sorry, yeah. Yeah.
And the pi to the
So four should be,
plus.
yeah. E power minus,
So this
yes,
is the
sorry,
test.
this is just the Euclidean action. Yeah, plus, yeah. Essentially, like you want that integral to be not well defined, and you're just interested in the perturbative expansion of it to see why it's going wrong. So what Lipperhoff suggested was, let's just take this, let's see if we can compute these CNs formally. And the way of doing that is to assume that, okay, let's just look at a contour integral of this function, of the partition function, C of lambda. But in a rather ad hoc manner, we kind of promoted this coupling to the exponent. So make the lambda n plus 1 to the e power minus n plus 1 log lambda. And what he proposed was doing a simultaneous saddle point approximation in both the fields phi and in the coupling lambda. So if you go ahead and do that, you can using del S, del phi. You're also, if you look at the extremum with respect to the coupling lambda, you get lambda star equals a finite number over n plus 1. That this Si is what he found to be the action of the Fubini-Lipperhoff instanton. So the action here with this inverted potential has a field configuration with finite action. In this case, in these units, it's 16 pi squared. And if the extremum lambda that you get from the saddle point approximation is given by the value of the action at this instanton field. And moreover, if you actually now evaluate Cn in the saddle point using the at this point, you can show using Stirling's that at large enough n, this leads to factorial growth. But what was important was the fact that, like, you showed that this factor A, the geometric one, is related to the instanton action. So even if I flip this sign of lambda here, or say, I mean, regular potential, sorry. Pi I.
R, capital.
Oh, capital. Oh, so you have both dilatation and translation symmetry here. Like for arbitrary values of R and X zeros, there's a family of solutions which give the same finite action. This is just telling you that, like, because this is like classically there's a scale invariant theory, I can have instantons at like arbitrary sizes. Right. Gamma 1 pi. You're looking at the number of diagrams. Yeah. I guess. Is good. You're trying to ask if I can replace S of phi with, like, say, the connecting functional, like the
Just what are the assumptions going here? Small n is very large.
If small n is, yeah,
I
right,
can imagine that some.
right, yeah. That like the rigor of this technique, I'm not fully sure of it.
Lambda
Small,
and
yeah.
n.
Yeah.
So lambda
Yes,
is like having
yeah.
a small h bar. Like 1 over lambda from this. Lambda star
Right.
star is 1 over little n. Or
Oh,
lambda.
no, yeah.
Okay, that.
Yeah, weak coupling theories, and like you want to go to as much order as you want. Yeah.
So also as well, yes.
Yeah.
But what is this instanton? Like, so here you don't have a master. Just an upside down.
Upside down one, yeah.
You typically when
Yeah.
so now it's right side up.
Yeah.
So what is this?
So I think in that case you can come up with a complex instanton.
Complex instanton.
So with the flipped sign, this is a real instanton. Like this is a real
So
field.
I'm just asking typically.
Right.
And the thing is interpolating between.
Yeah.
Here there is just one minima.
Right.
So what is the boundary condition?
Topologic.
Not a king type.
It's not a king type thing. Okay. There is one way of mapping this to a quantum mechanical Hamiltonian, where you kind of put in an ansatz phi, which is just dependent on the radial piece. If you do that, the field theory Lagrangian reduces down to like a inverted double well. So you can show that like this same field configuration reduced in the quantum mechanical case with like just R being like the radial coordinate being done.
X is R, X is a Cartesian direction.
X is a Cartesian direction, yeah. So X plus X0 squared will be R squared. Yeah. So there, like R becomes more or less like the time coordinate in the reduced quantum mechanical problem. You can show that lambda phi 4 actually reduces on for purely radial ansatz, reduces down to like an inverted coordinate. Exactly. Yeah. Yeah. So this balances both the centrifugal and yeah. Right.
Okay, so there is some.
The kinetic term will generate like.
But how will it generate phi? R in position. Laplacian in that will give you some 1 by R term. That so you have a 5 square term and a 5 kilo term. Important in this case to be 4 dimensions.
Yeah.
I think that's like mass square is a function of R. Right? But the other terms in the Laplacian also have derivatives. Yeah, so there's a del phi by del R square. Yeah. Oh, del phi by del. Laplacian even has a square of the first derivative, right? Square of the first derivative of it. There's always at least one derivative. So there's a del R inside the bracket and there's a path. Zero derivative.
With multiple couplings, you can't really scale it out. I mean, like if for instance, if there was like a lambda here, I can always scale out the field, right? I can just do phi x goes to phi x 1 over root lambda with just a single coupling. So as long as there's a single coupling, single interaction, I can always write the action in this form.
There is some instant torque.
Yeah, I can show you the details of it, but like for instance, like this is something which I've played with for a while, where you kind of posit an ansatz for phi, it's just purely radial. Yeah, here, unlike QCD or like Yang-Mills, there isn't a topological invariant, but you still have an instanton. Yeah. There isn't like a color index that you're correlating with the coordinate one. Here, this is purely, So QCD also you can do that, and I'm gonna get to that eventually. Like you can explore the existence of instantons there. Right. So when you'll have those zero modes explicitly coming in the measure d phi. So I'm gonna get to the fact that so this is purely classical. Like the existence of instantons, I don't really need at least in 5/4 theory, I don't need to look at quantum effects to see the existence of it. But the punchline which I want to get to is the fact that, like, say, if I couldn't do this saddle point approximation and all I really had access to was CNs, I could have inferred the existence of this instanton by looking at this growth factor A. It's telling me that there's a finite action field configuration which I'm missing, and that's the non-perturbative part here. And this is generally what the program for resurgence really is. You want to look at the all order behavior of CN and you want to figure out what these growth factors are and infer whether you are missing any kind of non-perturbative saddle in the path integral, which you should be including. Yeah. Yeah. I'm going to get to that. Like, I'm going to give a very simple 1D example of writing down like a complex integral and showing that like you can get the same form. It's the center of the instanton. R is the size of the instanton. Yeah. 4D. Yeah. Yeah. Right. Just the measure, like the distance from X and the center of that instanton. X minus X0. Yeah. Yeah. If you once you localize around the instanton, your D5 will have to account for the fact that there are these zero modes. So the argument goes through for theories where I have a single coupling, single type of interaction where I can critically write it of that form. With multiple couplings, I am not sure whether people have really understood what the high order behavior even looks perturbatively, because you have to have a sense of numerically which of these coupling is more dominant. How should I reorganize the series? For the time being, so far, most of the work has been done with like single coupling, no like couplings with like no mass dimensions also. Yeah. But what's interesting is the fact that like even if I flip the sign of lambda, I still get this kind of behavior. But instead of like being non-alternating, it's now alternating, so it can be desummed. So even though the instanton is not, there's no real instanton in the case where the potential is flipped, its presence is still there in the perturbative expansion of the partition function. That's where the interesting part really lies. Yeah. So I need to read a bit more on that one, which is the fact that like, say, if I flip this sign here, I would still expect some kind of series of this form, except like this SI would become minus there. There has been some work trying to see if there are complex instantons in 5/4 theory, whether that behavior.
If phi was complex.
Oh, if phi was complex. Oh, you're saying if it's not just a real field. Yeah. Yeah, two real field. I guess like the modulus of the complex field probably would still show this kind of yeah. I think yeah, even for a complex field, you probably can get this. The punchline was, and this is something which I'm gonna like use to eventually talk about Renormalons, is the fact that like what Lipatov showed was if I have this finite action field configuration, action of it dictates how fast my perturbative series blow up. I can infer the existence of this instanton by actually looking at how fast my perturbative series is blown, without having to look at the without having to extremize the action itself. And this is something which I'll try to reverse for. What Lipatov established was start with the action. If I have an extrema of it which has finite action, I can be guaranteed that the partition function or other observables in that theory will have a factorial growth, and the factorial growth will be dictated by the action of this non-perturbative saddle. Now, you can ask, is this all? Like is this, are instantons the only form of factorial growth that we know in field theory? And actually, this was even dating back to Tuft. He showed that, like, forget about the number of diagrams. Subclass of diagrams can actually even give you factorial growth. And because they were the subclass of diagrams led to the renormalization of the coupling, he termed it as renormalons. So what kind of diagrams am I talking about? If you look at QED, for instance, diagrams of these forms, which are known as bubble diagrams, where I keep on inserting these fermion bubbles inside a photon or a gluon propagator. You can evaluate these diagrams in normalized perturbation theory. And the form of these diagrams that you get, so Q here.
What is the meaning of?
Oh, this is just like I'm accounting for like attaching it here and attaching it there. So I'm going to get the same answer.
Parts of diagram, there's overall.
There's an over.
Like this chain.
Exactly. This chain has to be integrated over. So it's not just like a free one. So the reason why this chain needs to be integrated over is the integration itself generates a factorial growth. So what I mean by that is anytime I have these bubbles, once I normalize that at one loop order, I'm going to get a log, which is dependent on like the momentum that's flowing in here. Get a log n mu squared over k squared. I'm going to get an NF factor from the number of
K is the momentum.
K is the momentum that's flowing inside that in the bubble. Yeah. So I've kept n free. So this is like the number of bubbles that I've inserted. Yes. Yeah. And this factor of k to the 2a is dictated by the overall topology of the rest of the loop. Some factor dependent on the mass dimension of the diagram that you're computing, but it can be computed.
But in that setup.
Exactly. Yeah. These are known as like bubble diagrams where you kind of like insert the bubble chains and you integrate over them. So I'm just going to look at this subclass of diagrams. And if you look at these subclass of diagrams and you actually do the loop integral carefully, what you find is that like each bubble costs you this log factor in the momentum. And there's an overall factor of k to the 2a, which you can compute from the rest of the diagram. But if I can be general, if you compute this integral here, you find that you arrive at this factorial growth, not from the number of diagrams now, but by integrating over this log factor. So if you look at the subclass of the diagrams itself, even before you count the number of diagrams, subclass of diagrams, once integrated over the loop momenta are generated. Yeah, it's a form of like, I can increase the number n here.
One diagram is
Exactly. Yeah. One. I mean, to get the full normalization, I'll have to look at both of these, but both of them will generate. Exactly. Both of them scale like that. Yeah. So here, like I'm tracking just the NFP. So for QED, this would be all. Like if I was interested in just one loop QED bubbles, these are the only form of diagrams that I need to run. So A is the form factor for this diagram in the sense that like there will be some K dependence going in the other propagators as well. So if I evaluate that function fully, this is like formally like I can treat this formally as a two loop diagram, right? So if I reduce it down just to the integration over that variable K, I'm going to get a function which is which has some scaling with respect to K. And just to be like more general, I'm just assuming that these are polynomials. So you could do this more generally by having like f of k fully, but I can take that f of k and expand it at low k and large k, just to be interested either in the UV regime or the IR regime of the physics. And that brings me to a good taxonomy which people use. So for the full diagram, this would be f of k, what people typically do is that they either expand f of k in the small k regime, so in the IR regime, or the large one. And in either case, it reverts to something of this form. And that leads to two forms of factorial divergence, one coming in from the UV behavior of the diagram, one from the IR ones. So IR renormalons are the ones which people typically are more worried about because they are telling us something about IR dynamics implicitly. But you can have both, like you can have this factorial growth both from UV behavior of the diagram and or the IR one. So just to cover ground. Yes, positive. Yeah, we are in the Euclidean one. Yeah. So NF is the number of fermions I have. So like there's like NF fermions, NF Dirac fermions coupled to a U1. It's yeah. So you'll have to look at the full diagram. Yeah. Usually what would change is that the exponent would change. You could also get like k to the 2a times a log k squared piece. So like the UV regime can generate additional factorial growth. Yeah, if a is negative, yeah. Yeah, no, yeah. I'm assuming that like this is yeah, that the diagram goes to 0. And you can show that for the photon propagator here, you can construct a UV and IR finite quantity which has like k goes to 0 behavior, which is well defined. It's known as this Adler function, where you essentially end up taking derivatives of this diagram with respect to Q. And that's something which can be measured. Capital Q is the energy that's entering here. So
Right-hand side doesn't have it.
right. So I have cut it off with a cutoff here with mu, but I can be more general and do this over all Q. So the log n's here would be fully log n mu squared over Q squared times some dimensionless ratio k squared.
I should just think of capital Q on the left.
Yeah. But in principle, I can do the perturbative expansion not just at like the coupling evaluated at Q. I can do it at any sliding scale alpha mu. And the point here is that like the factorial growth is going to be true for the coupling evaluated at any arbitrary scale, either mu or Q, doesn't matter. Yes. It's in the IR and UV of, so as that question came, like I've simplified this a bit. What should be truly there, yeah, IR and UV of the two. The renormalan really only starts at two-loop order. Yeah. Okay. So these are the diagrams. Yeah. Oh, why? But the form of the factorial growth now is distinct. It's not coming in from the number of diagrams, but it's coming in from a subclass of diagrams. It's like integration over the Feynman diagrams is generating a factorial growth. The name Renormalon, I think, is due to Tooft, where I think he christened it that way because if you look at the kind of diagrams that go into the one loop renormalization of the coupling in QED, these chain diagrams are the ones which you need. You can alternatively also cast these integrals into an integration over the effective coupling being integrated over all scales. So that's why these were called renormalons, like we are from diagrams which renormalize the coupling itself. So this was the story for QED because the beta function, the leading beta function depends only on NF. Yeah. I think you'll need like at least two variables where I'm integrating over one of them to generate a factorial growth for the other one.
This integration. I have a 0 plus 0 dimensional field. Momentum to flow. Because you don't have any renormalization. Quantum mechanics you will need.
Oh, yeah, add like a massive Higgs ion. Would change is this factor here would now include like, but there's also the log would also now be more complicated to interpret. Yeah. I don't think it will be that simple to just integrate over K anymore, because you're gonna get a dimensionless function of M over Q. Where I think, yeah. So the UV renormals probably won't change. The IR ones would go away. Yeah, if I have a mass gap like this log is not going to be true for K less than M. Yeah. This is something which has been very actively looked at from phenomenology side, from for freezing the Renormalons. Right. Yeah. Right. Yeah. I guess with in those ones, if the log itself goes away, okay, it's very small ones. I'm no longer getting a factorial blow up, right? So phenomenologically, it won't be that pertinent. But yeah, that's an interesting question. Whether like diagrammatically, whether yeah, this should I mean, like what's gonna happen is that like it's going to be now a much more complicated function of not just one dimensionless ratio, but two of them. So understanding that one would be slightly more complicated. The mu is just the sliding scale of like dimensional regularization. It's just like my renormalization scale. It's just the scale which I choose to define my coupling at. I mean, so the loop is gonna have, once I add in the counter terms, that's gonna like the log is going to be a log of both the normalization scale and the physical scales.
It's not being integrated.
Yeah.
Why is it?
So I've put in the cutoff. You can do that integral over like all of K. Yeah. No. So this is just a schematic. This is just, I'm just like, if I put in the entire mathematical form, I'll still get this.
Like
piece,
you're
yeah.
doing this.
In dim bracket. Yes, it's full in dim bracket. So yeah. Yeah, so that's something that has been checked. This was something of a matter of debate in the 90s where people didn't really believe that this kind of factorial growths would happen. But they looked at Placket operators on lattice and evaluated. So they took the lattice results and converted into continuum schemes that you could expand to like 30, 35 loop orders. And the kind of behavior that they got exactly matched up with what was predicted from these diagrams. So it's inherently an issue of forcing your loop integrals to go into regimes where non-perturbative dynamics kicks in. But because you're evaluating it at the scale at alpha mu, there's a well-defined perturbative expansion. So you have to make sense of how you can add the non-perturbative input to these higher order perturbative data that you have. But that has been checked, like the existence of Renormalons via lattice has been rigorously checked. The range of for this, but sorry. I think there is some analytic continuation here to define that integral. Are you asking what A is for this particular diagram? You're looking at dx.
You can redefine log of, let's call.
Yeah. Theta.
Over k square of x over x.
Yeah. And the first papers were doing it for QED, and what they assumed would happen for QCD, which is something which hasn't been shown, and I think that's where our framework comes in and does a good job, is the fact that what they believed was if you add in ghost loops and the other ones, basically normalize the gluon propagator fully, the NFs here would be replaced by beta naught. This is something which hasn't been rigorously shown, and this is something which people call the naive non-abelianization hypothesis for this. So beta naught here is just the first one, the leading one. So for instance, if I am doing this for Yang-Mills, this would be just adding the CA factors and so on, adding the host, all of that. So this would just become the NF would turn into beta naught. And the way they've checked this is the function A that you get for these particular, the number A that you get for these subclass of diagrams matches up with exactly the NF behaviors of beta naught. For instance, for QCD or QED, A would be like 2/3. This is the large enough way of checking whether it's the running coupling. Exactly. Yeah. In the QED limit, but exactly. Yeah. So like essentially you want the integration to be happening over regimes where the coupling renormalization is very important. Yeah. So you renormalize the coupling, and this kind of behavior where you get this series where the growth is now dictated not by an instanton action, but by the first coefficient of the beta function, was what was christened as Renormalons. Something which I want to show is like I have these two sources of growths in diagrams which I know of. How do they look like in the Borel plane? Like I know both of them can't be resummed. Which one? Yeah. So this is non-alternating. The beta naught's positive here. That's gonna be a problem. For QED, it won't be a problem because the coupling is blowing up in the. But here, because we are interested in the aerodynamics. So you can go to two loop orders and so on, and I can show that in one of the backup slides. The behavior that you get kind of persists. So, but that's a very interesting thing to check, which is the fact that the large order growth is more or less dictated both by beta naught and the next one, beta one.
I guess that's the question.
Yeah, you can check. So you could check. You can check with like in the large enough approximation that like it's only beta naught which survives and not the beta one. So like the A here is really dictated by beta naught. Somehow one loop is special. Actually, like what's special is both beta naught and beta one. And the way I have made sense with that is the fact that like if I change the coupling definition itself, the only two coefficients which don't change under a coupling redefinition are beta naught and beta one. Everything else kind of it's a scheme. These are the only two which are scheme independent. This is true for a single coupling. I am not sure with the other one. Yeah. So what I want to now compare is that I have these two sources of factorial growth. I want to see how they look like in the Borel plane, and dive a bit into why they are very interesting. So what's plotted here is the Borel transform for CD. This 4 pi here is the. So large NF piece, and I replace the NF with beta naught. So I look at the
large NC and NF.
just large NF, not so for QCD, I can compute this piece in large NF, right? Large enough, it's not asymptotically free. So what I really want is this coefficient A, and I'll track that by NF. So I know the beta function for QCD at one loop. Exactly. Yeah. Yeah. With SU3. Yeah. No, that doesn't. So you like as I said, like this jump here is a very it's an but so the jump from NF to beta naught so far has only been assumed, and it has been checked rigorously via lattice, but nobody really has shown that like diagrammatically this is going to be true. You infer the existence of the Renormalons in QCD by looking at behaviors in the regime where it's like no longer like asymptotically free theory. That assumption is something which we wanted to actually explore and figure out how much of that was true, and that's what we understood via the path integral as to why this is dictated by beta naught and not by NF. Yeah. General field theories. Yeah. QCD. Yeah. So just to chart out the same diagram for QCD. So for instance, if I'm interested in the growth of the perturbative cross section of electron positron going to hadrons, that is something which I can actually compute perturbatively in field theory at large and large energies. And if I look at the large order behavior of this quantity, what they found was you get these series of Renormalon poles which are dictated by beta naught. So if I can go back. Yeah. But at large enough energies, the quark masses are going to be irrelevant, and I can expand it just in the coupling. Different masses, yeah. Even with mass, even with like
But you're saying you're
extreme, yeah. So I'm interested in the expansion of it in terms of the coupling when the coupling is weak. So that's going to be at like large Q. Yeah. Exactly. Yeah. But I'm still gonna see this n factorial behavior. And so like the poster child which we yeah, pretty much. Yeah. You can set the quark masses to 0 and you can still get this effect. So terminologically, what happens is the fact that like if you compute the large order behavior of the similar diagram in QCD, you find that like you get these set of Renormalon poles. So my growth was A beta naught. So my pole in the Borel action is going to be 1 over that. So it's going to be 1 over beta naught times some multiples. This 4 pi here is a normalization that we've chosen. So my expansion is in alpha s over 4 pi. This pole here is the first instanton anti-instanton configuration in QCD. So in QCD, due to topological numbers, if I'm concerned with vacuum quantities, I'm gonna keep the topological number also 0. So instanton contributions cannot give rise to large order behavior, but instanton and anti-instanton ones can. And the location of this Borel pole is given by twice the instanton separation. The pair is separated. But what's relevant is the fact that like if I did try to do the resummation, I'm gonna get hit with the Renormalon poles first than the instanton ones. Right? So they're going to be, I'm gonna have to deal with them before I have to even worry about instantons. And as somebody asked at the beginning, is this something that I see in areas of interest? And in particular, if you're interested in computing quark masses, this is a problem which plagues their precise determination, in particular for the top quark mass. So what I mean by that is you want to determine the pole mass for any heavy quark. But the ones which you actually, the mass schemes that you use for actually computing stuff is with MS bar. So there is a series associated which relates the pole mass to the MS bar mass. And what has been found is that this series in particular, for the top, bottom, or the charm, so the blue here are fixed order evaluations. So like people can compute Cn to say 2, 3 loops and 4 loops. The yellow are what you would predict from like a bubble chain approximation, like the Renormalon approximation for these growths. And they have found that the behavior, even at like 3 loops, for instance, at top already starts showing its classic Renormalon like factorial divergence blow up. So so if I wanted to use this series to do some precision phenomenology, in terms of like the pole mass, I have to be very careful about the kind of scheme that I'm using.
So gluons and
You for the top, once you're interested in the energy scales there, like bottom and everything else is going to be much, like you can treat them essentially to be massless. All one. So NF is going to be 5. Yeah. But the problem that arises is the fact that like you have to now be very careful about the kind of schemes that you're using to compute this at like 4, 5 loops and so on. Yeah. The pole mass in terms of the MS bar one. Yeah. Right.
Yeah.
So if I'm gonna have like a series which relates the pole mass to the MS bar mass, and this series itself is now gonna suffer a Renormalon. If you want to compute, say, for instance, decay rates of B mesons, something which is of interest for BSM folks is parameter like how accurately I measure the top quark pole mass, and the Higgs pole mass determines whether I'm in like a stable versus metastable universe and so on. So the pole mass of quarks actually do go into other quantities of phenomenological interest. And say, for instance, if I want to do precision B physics, I want to know the B quark pole mass to a rather reasonable numerical order so that I can predict decay of B mesons to a good accuracy. And this is where, like, if I want to do a 3 loop one, I have to be careful about the kind of quark pole mass I'm using or what kind of series I'm getting.
This is a statement.
The substantial, exactly. And like something which I have worked on, for instance, like where I have worked on like alpha S determinations from like precision event shapes at colliders. There too, you actually have to be very careful about like these Renormalon subtractions to get a very stable convergent result. Like if I'm going, so this is at the z pole mass. So if I want to determine alpha S mz, I actually have to be very careful about my convergence schemes. And without a convergence scheme, I don't get like stable results numerically. So this is a very pertinent practical problem. But theoretically, as I said, like this is also of interest just to understand like, okay, why does perturbative series rather weirdly in little bit. So I started with Lipatov's. Yeah. Yeah. Yes. Yeah. So the thing. So say if I want to compute that quantity, I have to have like a perturbative series. The series that I'm going to supply as a theorist better have convergence properties where it gives. Yes. Yeah. Yes. Yeah. You see, or for instance, like there are these. Yeah. Compare it with like experimental data. So the theory prediction better have like uncertainty bands where if I increase the order, the bands sit well within each other.
So this.
Yeah, it's ambiguities in the theory predictions which I'm gonna make, and I'm gonna do it at values of like the sliding scale mu, which are of order where alpha S mu is order 1. So I'm gonna be at like high energies. So this is the blue dots here. Sorry for the color scheme. Are like actual computations of this CN done to 3-loop orders. And the orange ones are the predictions from what you would expect from the bubble chain. You can see that like already at 3-loop order, they're tending to line up with each other for the top quark, especially. So even if you did a 4-loop or a 5-loop computation, you're gonna high. So it's
So things start break down at.
It's at low enough orders.
This is like the 3D statement.
137 would here it would be at it will be like 6th or 7th term and so on. So yeah, you have to be like I simplified the picture there. Like we use like tools like resummation, but like there even then to get like a convergent result, we have to be careful about these Renormalon problems there. So this is something which QCD precision phenomenology uses a lot, but they have their own set of ad hoc rules. And part of my interest in this project was to understand if you can ground those ad hoc rules into a consistent framework or see why that's happening via the path integral. So what I want to talk about here, so at the beginning, I talked about Lipitov's argument. I have an action, I have a saddle point, I get a finite action series, and that dictates that my series is going to blow up with that action. So what he showed was start with a saddle point of an action. You're going to get an asymptotic series which blows up. With Renormalons, what we really have access to is the series itself. Have some set of motivated assumptions where we can evaluate the operator or any other quantity of interest. And we see that it goes as n factorial with the growth coefficient being determined by beta naught. So what we wanted to answer was like, and this is something which other folks have also been trying to answer is there a sense in which we have a corresponding field configuration that's the same action? And if this field configuration extremizes some action of some form. So I want to go from the series and I want to find a saddle point of the action. So I'm going to reverse that order. And some of the conditions that this thing has to satisfy is, for instance, from Lipitov's argument, the SI was the action of the field configuration. So the growth rate here, beta naught over K, better correspond to the action of the field configuration that I'm finding. So I want to find S of some action which extremizes it at K over beta naught. So natural questions you can ask, is it the classical action? Is this something else? I'm looking at quantum effects because I'm looking at loops. Which Renormalon? Because I can compute this for some arbitrary operator. So my K is going to change. So I'm going to spoil it at the beginning. This is, you can show that like the action here, because we are dealing with quantum effects, is the one loop effective action. And this K here can be sorted out by looking at operator insertions of the particular. Yeah. So including all loops and normalizing it. Yeah, exactly. Yeah. The effect, one loop effective action with an operator insertion. And this operator insertion accounts for the fact that we'll get K dependent pieces, which are the operator mass dimension itself. The K here is the growth rate, beta naught over K. So for instance, for the photon bubble loop that I drew, K was 2. If you were interested in like the top pole mass, K is 1.
Like your A.
Yeah. But there A is full beta naught over K. So my series goes as alpha to the n factorial A to the power minus
A and F to the
yeah
little A.
little a.
Small. Yeah. Small A is like 1 over.
Yeah. So this K changes for like depending on what observable I'm trying to evaluate. Like if I'm looking at cross sections or if I'm looking at some 2-point functions, this will change. So you want to have something which not just does it for like a single K, but you want to account for like getting the saddle for arbitrary K. And what I want to do. Yeah, typically some integer. The reason why it is an integer is also interesting. And that's due to the fact that these operators, so what the Renormalon tells you is the fact that your perturbative series is telling you about the existence of a non-perturbative operator correction to that quantity that you're computing. So that operator's classical mass dimension is what dictates this value of k. So for instance, if I looked at the ambiguity coming in from this form, this would be lambda QCD to the power k. So k basically tells you what next operator do I need to actually include for my physical quantity computation, which is like marring my physical, like the first perturbative series at large orders. So I'm trying to be general here. O can be say G squared or something else. G is like the gluon field strength tensor or something. Yeah, so I am trying to here, if for here, O would be G squared, the square of the gluon field strength tensor. Does that answer? I can come to that. Yeah. So I'm taking the expectation value of some operator which I've built out of local fields, evaluating its expectation value in vacuum. Right. So the reason it comes at a gluon squared is the fact that like if I compute the ambiguity coming in from this Renormalon here 2 over beta naught, I get lambda, like the ambiguity comes out to be lambda QCD to the power 4. So that tells me that I should be looking at expectation values of operators with classical mass dimension 4. And the Lorentz invariant operator that I can construct even with quark fields, which satisfies all the symmetry, is just the field strength tensor squared. Yes, no, yeah, yeah, just yeah.
So what is the new definition of action with an operator? Going to explain it.
Yeah, I'm gonna come to that. Yeah. So what I wanna do next is like I essentially wanna get up to this point. Yeah. So I'm gonna take a just lay out my assumptions first. The first thing which I want to answer is why Borel transformations, and this is right due to the fact that like saddle point approximations usually lead to series which is asymptotic series, which can be Borel summed. And this is true for exponential Laplace integrals, which are very common in physics, like path integral or like one-dimensional reductions of it. You're almost always looking at single coupling, single interaction forms would give you something which looks as e power minus the action over the coupling. And the way we work this out is like, say, for the one-dimensional case, we start with an integral of this form. Alpha here is the coupling. I can evaluate, I can extremize this action, expand the action around that point. I'm going to call that Z star. And if I do the saddle point approximation to this function f of alpha, I find this form where I have these higher order terms, of which I can now rescale. So if I rescale Z here by alpha appropriately, what I get is a series which is asymptotic. So I can expand this out in alpha. I'm going to get a factorially divergent piece. But one can ask, like, where exactly am I doing this Gaussian integral? Am I doing this over like real Z's, or is there some other contoured path which I have to be careful about to make this converge? And the theory of complex analysis tells me that like the Gaussian integration here has to happen along a specified path. And in particular, if I complexify Z, this is the path where like the real value of the action is rapidly increasing. That's due to the minus sign there. And this is what people call as a thimble. It's a path in field space where my action is rapidly falling off. Yeah. The contour, yeah. I'm gonna. This is like I'm just trying to. I'll get to that. Like usually, you're correct that like I want to start. You have to start with a contour. I have to decompose that contour in terms of the thimbles. Yeah. So like an example which works is, for instance, like a 1D example of a double well, where I start with this action where I have like these two saddles, like 3 of them at plus, minus 1 and 0. I can actually do a saddle point approximation of this exponentially weighted action around, say, z equals -1. This would be what I mean here is I'm going to take e power minus sz over alpha. I'm going to do a saddle point approximation around z equals -1. If I do that, I get this series here in alpha orders. I can Borel transform it. And what I do find is that if I take this Borel transform and do the inverse Laplace transform of it, we find the integral not along the real line, but it's along the thimble passing through that point, S of C. So if I plot this out, the x-axis I have the real coordinate of C. On the z-axis, I have the real value of the action. To curve here is the path along which the action rapidly along this saddle C equals -1. So if I evaluate the perturbative series along this point to extreme high order, do the Borel transformation, do the Laplace, do the inverse Borel transform. So that's just integrating this over e power.
This for either side.
Either side. So the problem is so here the I epsilon is problematic because I started with a series which is not alternating, and that's due to the fact that the thimble from the z equals -1 is hitting the thimble at z equals 0.
Yeah, but I'm just asking when you draw this arrow,
Yeah.
I epsilon sign doesn't matter.
So the I epsilon prescription is just whether my thimble goes down or up, and that can change.
What I'm asking, let's say plus.
Yeah.
On the thimble is unique.
The integral. Yeah.
Plus or minus I epsilon doesn't matter.
Oh, no. Let's see. So my thimble here, the real action increases either end. So the problem here is here the integration around the thimble is fine locally around the saddle, but it hits another point.
All the
If your thimble is well defined, the integral converges.
so what
Okay.
does this mean? I'm just asking,
So,
what is the last arrow?
Yeah, okay. Yeah, maybe I shouldn't have started with this example. Say if I could do the Borel summation and I didn't have an I epsilon prescription and it was a well-defined integral, the result of inverse Borel transform is going to give me the integral along the thimble. So if it's a well-defined thimble. In this case, what's happening here is what's known as a Stokes phenomena, where I have this pole which I can't integrate over. And the pole shows up where I have a thimble from one saddle hitting the thimble from the other one. So if I flow from this point here, I'm tracking where my real part of the action is.
About the reason.
About the the plus minus I epsilon is telling you that I'm gonna get an ambiguous Borel summation at the end of it. This one, yeah, sorry, yeah, this one. If I had a well-defined Borel transformation, it would be true. In the case that I can't resum it. If I do a lateral Borel transformation, like I avoid the pole, I'm still gonna get an imaginary piece, and the imaginary piece corresponds to how I choose to continue my thimble once I've hit the Stokes point. Does that make sense?
Does the plus I epsilon corresponds to going along the blue line?
Exactly, up, yeah, exactly, right. So for instance, if I wanted to do this integral along the real line, my thimble decomposition would be I start here, hit this point, I go down, add the red one, and then add back the whole thing. So the imaginary parts from the lateral Borel transform will all cancel out. So the punchline here is I do this, the blue term, the blue piece, the Borel transform from the first saddle is going to give me an imaginary term. Similarly, I'm going to get an imaginary piece from the expansion around the green one, z equals 1. And if I account for the expansion around z equals 0, that integration contour is pure imaginary. the imaginary contributions from all three pieces are going to cancel off and give me a real integration at the end. So what I want to get here is the fact that like lateral Borel transformation, where you're ad hoc avoiding the pole and adding in imaginary pieces to a real quantity, has to be supplemented by the fact that you know what your original integration contour is. So that at the end of the day, you're really computing like a real integrand across the real line. And the fact that I get a Borel transformation which I can't resum is telling me that I'm hitting a Stokes point. And I have a choice of like either going above the real axis or below the real axis. That choice is completely arbitrary. And that's due to the fact that like I chose here that the blue line goes downstairs, adding like a small I epsilon to my coupling. I could have changed the I epsilon and my flow would have changed upwards instead.
Understand this final equation that
Yeah.
what you're saying.
Yeah. So in the case where if my Borel resummation works, if I can do the Borel transformation,
So
then you have no problem.
supposed to know.
Yeah, but
Here what you
here,
one contour, let's say
yeah,
some I epsilon and that's just the real life.
Yeah.
Then you decompose
yes,
each of them.
right.
Which is a two. So if that was the case, the one in the center. Here it's coming with some polynomial. But just decomposing the real line. The blue and the green one with one. Here he's doing something different then. The way to think about it, you take the real line, compose it along the real axis and then down. Union is, and this blue line is given by pattern plus half of the red.
Right.
Go up on the red cancels out. Just get blue plus the solution of what you said.
Right.
But here a stronger statement is being made that now do more to the red and green side. Add some red, then you get some sensible result.
Not quite. I'm like this here, this B0T is basically just the saddle point approximation around z equals 0, which is like a inverted Gaussian, right? So I'll have to complex continue that one to get that form. It's like a maxima.
One way of writing the answer.
Right.
In the song.
Which
without
would be
these Borel transforms appearing.
right.
And take the any function,
Yeah.
Starting contour and you try to ask some time.
Right.
If you just play that game without talking about Borel,
Right.
you will not get a contribution from the
Right.
are adding the
Let's see. But the contour decomposition, even for the airy function, changes depending on like what my coupling is.
fix this contour, that's the real act.
Right.
Fix this one.
Right.
Figure this fix.
Yeah.
In that, try to do the steepest descent.
Okay.
The red one will not count. Just the normal statement that unstable saddle points that are on the contour row. In some sense, in the sense of as descent analysis. Here you are mixing that with the Borel transform.
Right.
And doing something.
I mean, but what I'm getting at here is the fact that like, hey, okay, this Borel transform here itself is I can't really do it, right? Like I'll have to change it. Yeah.
Yeah. And get some other result.
Right.
The Borel transform.
You're saying that the blue and the green added together will just give me the full answer, and I won't have to. Okay. I mean, so the punchline which I wanted to get at was the fact that like I have to be careful about with caveats. You have to be careful about how the original integration contour decomposes, but it usually decomposes into some weighted sum of the thimbles. And the integration of the action along that thimble is basically the Borel resummation of the perturbative expansion around that saddle point. So if I do just this one here, B1, I'm just going to get the integral around the blue line. If I do the Borel resummation on the green one, I'm going to get the thimble along the green one, and so for the red one as well. So, and what's interesting is the fact that like the existence of this maxima at s equals 0 is inferred from the fact that like my Borel transform at t equals a fourth, which is where the action S0 is just 1/4. It's telling me about the fact that like the perturbative expansion is going to go slightly haywire due to the fact that there's an unstable maxima on my integration point. We have a rather, so for the one-dimensional case, you can be more general about this, and you can derive what's known as like its duality between the integration variable z and the Borel transform. And what we find is that the Borel variable t more or less corresponds to the action along the integration variable. T becomes the action S of z, and the Borel transform B of t is basically a sum of the integral variable along the level sets. So B of t is just sum over z, where I restrict z to be the inverse parts of S of z equals t. This is a Borel. This is the sense in which the Borel transform complements the action of the field of the variable. We can do this for this one-dimensional case, where say for if your action t is less than a fourth, is more than a fourth, I have two solutions. Z less than a fourth, I have 4 solutions of it. And if I use this Borel action correspondence to construct the Borel transform, I get this form here, which is exactly equivalent to the sum of the Borel transforms along all 3 different saddles. So the Borel action correspondence is a rather neat and fast way of like getting the Borel transform for these one-dimensional integrals. What I'm going to use, what I'm going to do over the next couple of minutes is elevate this to the field theory or quantum mechanical examples as well. So this could be either a delta function or a theta function, depending on our normalization for of the overall alpha there. But what we have is that in the one-dimensional case, the Borel transform corresponds to an integration over a volume. So B prime T is basically like the density of fields with action less than equal to counting like the volume up to a level set. And for higher dimension variables too, you can actually also make this case. B of t is just an integral over the integration variables, where you integrate only over the region where the action is less than equal to the variable t. And pictorially, one way of visualizing this. So for instance, if I'm looking at S of z as the S is bounded block, yeah. So if, for instance, I look at the height function of this torus here, and that has the action, B of t would be looking at like the level sets of along this manifold of C. What happens here is that as I increase this level set, at points where I have this saddle, that's where my Borel transform B of t now starts showing non-analytic behavior. It starts having discontinuities, it starts having poles and so on. So the level set of the levels, if the level set splits, that's where I know that there's going to be some interesting behavior in the Borel transform B of t. I'm going to have like either 2 branches come up, or there's going to be some way in which I have to specify which B of t I have to follow. And the red points here along in this pictorial example are where the saddle points of the height function actually happens. You can put this to action. Exactly. Where?
But the point is that
Right. It can. Exactly. This kind of, yeah. Or you can have fields where suddenly the volume of field space actually blows up with the same action set. And that's a couple examples that I'm going to show. So the instanton case is more or less like the pictorial height function which I showed, where you start with the action and your Borel transform actually blows up when you hit the saddle point. And this is the example for the Fubini instanton. This is true even for like perturbative series such as the anharmonica oscillator in quantum mechanics. If you look at the perturbative series there, the flipped potential admits an instanton. So the series, this SI or A for the anharmonic oscillator shows the same behavior. And I have a second case where your action can actually just asymptote. So an example for this, where the integral actually doesn't converge, but you can still write a perturbative series and compute its Borel transform, is this form here. This is an example of, for instance, the double well energy levels. So if you look at the perturbative evaluation of the double well in quantum mechanics, the Borel transform for the ground state energy shows this kind of classic Borel poles at twice the instanton actions. True even for the instanton anti-instanton pair in QCD as well. So this covers the classic cases. What's nice is that for the Renormalon, there is a second case where B of t can diverge at finite z, where all of a sudden you have a large field space coming up all with the same action. What do I mean by that? I can formally look at this integral of this form. I'm going to use two variables now instead of just one. S of z and rho have been named with intentions at the end. You can formally evaluate this without specifying where the region of convergence is. And this has this kind of classic pole-like behavior for the Renormalon. And if you look at the saddle point of this two-dimensional action, you do the integral over one of the rho, you do the rho integral, yeah. And that generates this pole, yeah. I'm like, formally this doesn't converge, like it is a linear integral, I have to be careful about that, but like at the formal level, I just want to, like, I can expand this in alpha and I can get a perturbative series. Exactly. So you get this finite action solution. If you plot this out, you see that there is a saddle along this rho and the, so S as a function of Z and rho, you can see that you get this saddle here. This degeneracy that you alluded to arises from the fact that like at one loop fx, I'm going to break the classical scale invariance. And these terms here are basically like analogs of one, the classical action. And the second term is breaking of dilatation symmetry. So this completes the picture, which I want to accept. This is just the 2D example. This is a 2D example. Yeah. Right. The Borel transform for this integral in terms of alpha. Parvati, yeah, exactly. Yeah.
Point solution is
Right. Yeah. Right.
not get any one loop factor at all.
Yeah.
And part of the continuum.
Yeah. That's so. What I want to do is that I want to start with this action function and I want to construct the contours fully. Right. I want to complexify both rho and z, and I want to look at the regions of convergence.
Minus z.
Right.
Okay.
Yeah.
Back diagram.
Also, a beta function is gain very an integral along those things.
Yeah, I mean, so I can go to the field theory thing directly. Like I started with the 2D one just for pedagogy. So I'm going to compute this operator expectation value, path integral. I'm going to be general, evaluate only operators with like some classical mass dimension delta O. I want to write down d phi, and I'm going to use these spaces where I can kind of factor dilatation and translation mode separately. So my measure d phi is now going to have an integration over like the translation pieces and the dilatation one. If you do the integration over the translation once, due to the classical scale invariance of this theory, you can factor this entire thing out into this form where I have integration over the other modes. I factor out the integration over the dilatation mode, where I get this factor of r to the delta O just from the mass dimension of the operator. And the critical part is that the power minus 1 over alpha now just becomes e power minus 1 over alpha of r. And if I just use the one loop running, this splits into alpha of mu times beta 2 beta naught log r. So if I change, if I write rho as log mu r and write t as S0 an, this reduces down to the exact 2D form. Skip this a bit, but what I really mean here is I want to change my integration variables to S0 an, call that as t. The classical action is more or less like the Borel variable. And this log mu r is this dimensionless variable rho. This b tilde t here is where I do the integration over the rest of them. This is happening over the classical action. And you can show that this also has singularities, but these singularities are at the classical saddle points. So this is including the instanton poles in the Borel transform.
Just say what the integration.
So in the final integral, I would have to, so you start here, I start with like log mu r to infinity. So I'm looking only at the IR ranges here. So I have this scale R0 and infinite. This would be, say, for instance, dictated by log of mu r, yeah. Low scale to, yeah. Some fixed scale to infinity, yeah. But once I start looking at it as a 2D integral, the symbols will be dictated just by the action itself. The region of convergence of rho will be dictated by where the complexified. Yes, yeah. So that we do check.
This 1 over, this set. E to the minus x, to the minus ax.
Right.
Go to infinity and a.
Right.
That's not coming from some saddle point, it's just coming from
the boundary one. Yeah.
Boundary.
The boundary of that integral, yeah.
And that's the only way you will get that 1 over saddle point and 1 loop. This is just a delta hump.
Right.
The only way to do this,
yeah.
You put an I.
Yeah, you'll have to, yeah.
Have a delta hump.
So that is where like part of, so I can get to that one. So say I start here, right?
Yeah.
I can now look at what the symbols for these ones are. And you can, what we find, okay, I can come to this later, where you can show that like this works for QCD as well. You can compute the leading Renormalon in the Adler function, where you take O as trace G squared, delta as 4, you get that back. But coming to Raghu's question of like what the actual integration variables are, I start with this action S of T and rho. This is, I want to come up with like, I want to complexify both T and rho accordingly. And you get the symbols in higher dimensions are what's known as like the middle real dimension contour here. So you complexify both T and rho. it's a 4D complex space, but like the real middle dimension should be 2D. So the complexification here works as t and rho both have the same imaginary value. The thimble through t equals 0, rho equals 0 are these side planes.
That's not a saddle point.
That's just the endpoint of that integration. Yeah. So I'll have to look at the boundary contributions and I have to include that one. But the red one, which is where the saddle point is as you said, it's along pure imaginary ones where you have these coordinates. You really are going over like the contribution from that saddle point is pure imaginary.
Yeah. Going along the
pure imaginary direction. In rho, I think so. W is R. It's actually a mix. So in this parameterization, the imaginary direction is both along T and rho, and you have to satisfy this condition. So this is just rigorously asking that real values of S rapidly decrease, but preserve imaginary value of S. So im S equals constant is still the defining equations for thimbles in higher D complex spaces, but you just have to be careful about how it works out in terms of the dimensions. We can wrap up in like maybe a couple more minutes. Oh, okay, sure. I can wrap it up really quick. So the punchline that I want to get at is the fact that like back to that slide. I didn't need any kind of NF to actually show that this was beta naught. And that just came about from scale invariance in my theory. So beyond diagrammatics, just from looking at the path integral and accounting for the scale anomaly is telling me that like I'm going to get these Renormalon saddles, which are dictated by the first coefficient. You can ask me about the two loop pieces, but even with the two loop contributions, you get the same kind of singularity, except instead of being a pole, it just now becomes a branch cut. So you just have to be slightly careful about how things work. The second thing is that by finding this as a saddle point and figuring out and really working out what the thimble looks like, you can now start answering the same kind of questions where the green, for instance, would be the perturbative contribution to a quantity that you're computing. And doing the integral along the green thimbles gives you the same result as doing a lateral Borel transformation by going around that pole. So you get a real piece and an imaginary contribution. And the imaginary contribution kind of is of the same parametric form as the new saddle. What we still need to show, and this is where we've been working on for a while, is the fact that like beyond just this new thimble, we need to get the other pieces as well. Like if it's really like the 1D instanton case where I start with like a single saddle, I have an imaginary thimble which gives me twice the imaginary piece that I get from like Borel resummation. And I have a third saddle beyond that which needs to be accounted for. So evaluating this in full glory is slightly more difficult. So far we haven't accounted for the DAN integrals and tried to be slightly general. But we are working on field theories, particularly two-dimensional 1+1D theories which have the same characteristic as QCD, where we can evaluate this thimble to a rather decent degree and map these thimbles to what people call as operator product expansion terms in QCD phenomenology. So the operator product expansion in QCD is slightly different from the CFT literature, where it's not a small distance expansion. It's a lambda QCD over the high energy scale expansion. And the first leading term is usually what people compute using Feynman diagrams. That would be what the green thimble is. The aim that we have is to nail down what the red or the new Renormalon thimble really gives. Is it the higher order pieces in the OPE where there are some imaginary contributions? Why are they imaginary? Are they telling you some non-perturbative interplay with the perturbative pieces? So conclusions. Wrap this up real soon. The punchline that I want folks to take is that the Renormalon can also be thought of as the instanton, except now it's a saddle point of the one loop effective action instead of the classical one. So there's a non-diagrammatic way of understanding this high order diagrammatics pieces that we are getting. future work in particular, which will need, which we have been working on, is trying to use these principles from resurgence and connect the full trans series associated with Renormalons in field theory to operator product expansions, which have been practically used in phenomena. Hope is to basically give a rigorous or physics level of rigor justification for the use of operator product expansions in precision phenomenology to deal with Renormalons. I'm here till tomorrow. Yeah.
Final statement, I got a bit more. Factorial roles coming from the diagram.
Right.
They sort of correspond
To a
this red sheet.
Yeah.
that you're drawing
No,
this
so the
particular-
factorial ones are from like the boundary, the green ones which I sketched, where if I do the lateral Borel transform, those are from the boundary, which are giving me an index.
The same way that the large order rows of that series,
Yeah,
you're saying is some kind of due to do the red sheet.
red sheet, exactly. The
How do you
present.
see that the red sheet? For that you have to do some this
So
limit
the
of argument. Right?
yes.
Or is that still?
So we just looked at the saddle point to see that like these corresponds to exactly the same kind of behavior. What we did was we evaluated the saddle point along the red dot. That gives us a pure imaginary contribution, and it has the same form as what you would get from the imaginary contribution from lateral Borel transforms along the perturbative diagrams. The hard part right now is actually fixing the coefficient and checking that the coefficients actually match up. So far, what we are getting is like the instanton picture where you get twice the value. Whether there's a further saddle beyond that, beyond just the red one, is not clear. But that's something that we have been working on. My flight's at 5, so I'll have to probably leave around like 2:30. Yeah. Sure. Is there a canteen nearby?
Yeah,
Sure. All right, sure. Okay. These need to